pale ring of light crowns a distant world. The sunlight there is a whisper of what we know. Yet the rim glows like a filament held over a cold sea. A small spacecraft once swept past, then turned to look back. The world replied with a halo. Haze stacked in sheets. Mountains etched the glow into combs. And a bright basin shaped like a lopsided heart lay across the surface, as if it were a sign we should learn to read. Why does a place so far from the sun look so alive? Why does a surface so cold carry marks of motion and change? Stand with that image until your eyes begin to adjust. The sky is not truly blue, only the memory of blue in a very thin air. Shadows run long. Peaks jut like blunt knives from plains that seem poured, not shattered. The light is weak, yet details stand out with a stubborn clarity. This is the paradox. Dim light should hide form, yet it reveals it. Thin air should do little, yet it leaves fingerprints. If such small forces can sculpt a world, what has time been doing there while no one watched? We move across the heart-shaped basin, a depression as broad as a small sea, paved with nitrogen ice. Fresh frost reflects like powdered glass, so it looks young. The surface breaks into giant polygons, smooth within, ridged at the seams, as if the ice were slowly turning over in cells the size of cities. The edges creep, fracture, heal, then creep again. From orbit, it looks like skin over a slow breath. If the top is in motion, what pushes from below? If the top is frigid, what warmth could organize that dance? You know how a winter window blooms and fades as warm air inside meets cold air outside. Here the air is so thin that a sheet of paper could outweigh a column of it. Yet it still moves frost. Nitrogen turns to gas in weak sunlight, slides as a wind along low slopes, then falls back to ice and shade. The basin becomes a trap for that flow. It fills and empties, opens and closes, day by day, season by season. The plane pulses, not like a heartbeat in flesh, but a cycle with timing and reach. If a plane can pulse, can a climate exist at the edge of the sun? We step to the mountains, rough, high, and strange. Their flanks are not carved by liquid water. Their forms do not match the clean cones of fire and ash we know. They rise like broad shields with collapsed crowns, or low domes with broken rims. In places, the ground swells and sags as if it once held a soft core that gave way. You have seen a pot on a stove go from liquid to crust, from smooth to cracked, from swollen to sunken as steam slips out. On this world, the heat is weak and slow, but time is long. What forms when slow heat meets long time? Now look up again. The haze is not one veil. It is a stack. Bands upon bands wrap the sphere. They bend over peaks and dive into valleys. Backlit, they light up like the ribs of a lantern. On cold mornings in mountains on Earth, you can see fog in layers like that. Some higher, some lower, all thin, all real. Here, those layers are a planet-scale map of temperature and chemistry. When the sun slides behind the rim, the stack goes bright and sketches the shapes beneath it with lines of light. Light writes the story on the edge. The edge writes the story back to us. If light can write, what is it telling us about the ground and the sky? Simply put, this place behaves like a spare room with a cracked window and a cold floor, where thin drafts rearrange frost each morning, and the furniture itself seems to have shifted an inch while you slept. That image is a human-scale echo of something slow and enormous. Frost moves because it must. Haze stacks because the air cools and warms in bands. Plains change because ice, under stress and faint heat, can flow as surely as a glacier flows on Earth, only with different chemistry and slower steps. If we can map those steps, we can hear the rhythm of the world. There is a second riddle hanging above the first. A large moon turns in lockstep with the world below so that the two always face each other. Their center of mass stands in space between them. a strange duet. The moon wears a cap of red at one pole. It is not paint. It is chemistry grown from sunlight and time. Where did the raw material come from? One idea says vapor from the world below climbs, escapes, and drifts across to settle on the pole of the moon, where cold holds it and light cooks it into color. A wind that begins as frost may end as red dust. If material crosses that gulf, how strong can this two-body system be? Return to the heart of bright ice. It sits near the equator but behaves like a climate pole built by geography. It gathers vapor like a trap. When sunlight touches it, the trap opens. Gas flows outward toward colder ground. When night returns, the trap closes. Gas rains down as frost. This is not weather in the way we count storms. It is a system of exchange, a slow breath that drives the whole plane. What does a slow breath do over millions of cycles? What shapes freeze into place? What signals do they leave for us to read? A label will not help us much here. Planet or not, a planet is a side trail. Names are tools. We are studying a world with active surfaces, with an atmosphere that plays tricks with light, with a companion that reveals chemistry across a gulf. The label does not move a grain of frost. Forces do. If we chase labels, we lose the pulse. If we chase the pulse, we might find the source of power that keeps it going. Power in deep cold does not come free. Sunlight is meager. Impacts stir and pass. Tidal tugs between the pair can do work, but they are steady and small. Inside, heat remains from the start, and more comes from the slow decay of heavy elements locked in rock. If the crust shows long rifts, if the ground looks stretched rather than crumpled, if plains rise in one age and slump in another, then the interior is warm enough to push and pull. Warm enough for what? Exactly. Warm enough to keep a deep layer from freezing solid. Warm enough to hold onto a lens of water mixed with antifreezes like ammonia and salt. Warm enough to store memory. Not in rock, but in liquid sealed by ice. We cannot drill there. Not yet. We must read shadows, colors, and shapes. We time how thin air dims a star during a distant pass. We measure how sunlight scatters off grains we cannot touch. We follow the parade of dunes that should not exist and see where they lead. Every reading is a clue, and every clue points back to the same crossroads. There is more energy inside than we guessed. There is more choreography between surface and sky than we expected. There is more reach in this small duet than in many grander systems. Why should this matter to anyone who does not carry a notebook of spectra? Because restless ground redraws the boundary between dead and alive in our minds. Because a frozen ocean, if it exists, is still an ocean that can store heat, salt, and time. Because a thin atmosphere can build complex structures without storms. Because a red cap on a moon teaches us that matter travels, bonds, and transforms in silence. Because the far edge is not empty. It is a laboratory that gives us fewer variables and longer baselines. We are not after spectacle, we are after process. Hold the opening scene again. The backlit rim, the stacked haze, the bright basin that seems to pulse. Your own breath slows to match the idea. This is the first act in a patient chase. The clue is light that makes little sense. The contradiction is motion where there should be stillness. The first hypothesis is a heat source buried under miles of cold. The chase is to test that idea against everything the surface can show. The reveal will not be a single sentence. It will be a pattern that fits across many small facts. Two scenes wait just off stage. One is a set of broad shield-like rises that might be silent vents, traces of a cold form of volcanism. The other is a small body at the edge of the system, a contact binary shaped like a snowman, fused so gently that its surface stayed intact for billions of years. Both scenes talk about heat, time, and assembly. If the world of haze and heart is present tense, Those two are memory. Memory is where we test our models. Memory is where we see if the chase is on the right road. We will test the light against the ground. We will test the red cap against the chemistry. We will test the planes against the math of convection. We will test the mountains against the logic of eruption without fire. At each turn, we will ask why it matters beyond a single world. Every answer will point outward. If slow heat can organize ice into motion here, it can do it elsewhere. If thin air can structure itself into a cathedral of layers here, other thin airs can do the same. If matter can cross from world to moon with such reach, then exchange is a rule, not an exception. The question that opens the gate is simple. Why does a faint place look vivid? The answer we will end with will not be a single cause. It will be a network. That is the kind of answer worth chasing. It changes how we look at small worlds. It changes how we classify what counts as active. It pushes on our idea of habitability by moving the arena underground. Most of all, it makes us adjust our sense of time. Processes that crawl can shape entire landscapes if they work without rest. Our lives are short. These processes are patient. Patience writes in large letters on ice. Now lean close to the edge of that halo again. Thin air makes thick geometry when the sun is right. The stack of haze bands acts like a relay, carrying a signal from ground to sky and back. The basin answers by exhaling when warmed and inhaling when cooled, moving frost like a tide. The companion moon nods in step, collecting a dusting of organics at its pole, a subtle receipt of exchange. The whole system is a quiet machine, slow, precise, and stubbornly alive in its own way. We read it by light. We test it by shadow. We judge it by change. If a heart of ice can breathe, what else can a frozen world do when no one is watching? If a veil of light can reveal the bones of a landscape, what secrets wait in the narrow space between world and moon? If a museum of the early system waits beyond, what exhibit label have we misread for years? We will ask. We will map. We will compare. And we will let the evidence tell us when to believe we are right. The world will not hurry, neither will we. If this opening moved you, like and subscribe to the Quiet Universe channel. The first clue is not sound but shape. A gleaming basin sprawls across the hemisphere, bright as chalk, bordered by low scarps and scalloped ridges. Its interior parceled into giant polygons like a cracked glaze. Viewed over hours, the seams look as if they creep, seen at sunset. Faint mists lift at the edges and settle again when the light slides off. If the camera could listen, we would swear the ground is inhaling and exhaling. Why does a bright basin behave like a lung? Look closer at the fabric. The plane is not water ice. It is dominated by nitrogen ice, a material softer at these temperatures than rock, capable of flowing if nudged long enough. Each polygon is smooth within but ribbed at the boundary. The way convection cells on a stovetop organize boiling soup into steady, shifting plates, yet nothing boils here. The sunlight is a fraction of a fraction. The air is as thin as a sigh, and the average surface temperature would freeze our instruments. What can drive motion where heat is so faint? The contradiction sharpens in the margins. To the west, dark flow like features curl around promontories as if a syrup once crept there, then froze. To the east, pits and troughs hint at slow sinking, like a heavy blanket settling under its own weight. If this is a dead world, it writes curiously lively sentences. If the surface is a statue, it has somehow rearranged its pose. If the crust is a shell, some force inside has pressed against it long enough to leave a fingerprint. The puzzle is not that change occurred once, but that it seems to be occurring now. At its core, the working hypothesis is simple. The basin acts as a climate pole made by terrain, a cold trap that collects vapor when sunlight is weak and releases it when sunlight returns. Nitrogen sublimates where it is brighter, flows as a tenuous wind along low paths, then condenses above the basin as frost. Over days and seasons, the plain fills and empties. lowering pressure here, raising it there, shifting weight across the surface by a hair, and then by another hair, until the sum of hairs equals a shove. That shove feeds slow overturn within the ice. Convection cells form, their tops cooling and sinking at the seams, their hearts rising where the center warms a little more. The cycle is not frantic, it is patient. If pressure is almost nothing, how can winds move frost? Because time multiplies small pushes into large work. The lung metaphor is not an ornament. It predicts behavior. A lung has a cadence. It opens and closes. It is sensitive to temperature, to pressure, to posture. The basin should have a cadence too. When the subsolar point moves north or south, the plane should exhale more on one side, inhale more on the other. The borders should migrate like a slow tide. Pits near the center should widen and narrow with the seasons, their rims abrading and healing on schedules we can check. What timing would such a breath keep? We can test this picture. Map the albedo at high resolution year by year and look for lateral drifts at the boundaries of polygons. Track the sharpness of their seams, which should grow when the center is warm and blur when the center is cool. Measure the pressure of the thin atmosphere during stellar occultations and compare with the season. If the basin is exhaling, pressure should rise ever so slightly just after local noon and fall before dawn, with asymmetries tied to topography. Compare the pattern with thermal models that include the real slope of the rim and the real depth of the depression. If the breath is real, models that ignore the basin's geometry will miss the observed phase and amplitude. If the breath is geometry-driven, models that honor the shape will get the phase and amplitude right. This matters because it resets how we define an active world. We have been trained to equate activity with thick air, rain, and plate tectonics. Here, activity looks like frost that walks and ice that flows without rivers or plates. We need words and tests that do not require storms to admit motion or volcanoes to admit heat. The lung gives us those tests. There is a deeper tie that may fix the rhythm. The world and its large moon rotate in lockstep, two dancers facing each other forever, their shared center of mass hanging between them. That duet freezes stress patterns in place. The basin sits where it sits not by chance, but by the combined pull of gravity and the relief of the crust. If the basin's mass deficit is large, the world may have rolled slightly so that the depression faces the moon, finding equilibrium where tides are easiest to bear. If mass migrates in and out as frost comes and goes, the location of maximum stress will oscillate around a mean, rocking the crust by millimeters, then by centimeters, across long cycles. If the heart is anchored by tides, what fixes its rhythm? The duet does. Think of it like this. A shallow bowl rests on a soft tablecloth. You sprinkle sand into the bowl, then pour sand out, and repeat. The cloth sags when the bowl grows heavy, then lifts when the bowl lightens. If the cloth is thick, the changes are small and slow. Now imagine this happens for years and centuries. The folds of the cloth at the bowl's edge will creep outward and inward, and any pattern painted on the cloth will drift. The world's ice shell is our tablecloth. The basin is our bowl. The frost is our sand. That is how ounces of vapor make miles of ice move, as long as the clock hands are patient. The chase begins by asking for clean predictions. If sublimation drives winds that feed the basin, dunes of nitrogen-rich grains should line up along consistent directions near the exits, their crests obeying the vector sum of slope winds and basin breezes. If convection builds polygons, their diameters should scale with the ice thickness, letting us estimate depth from planform. If weight shifts seasonally, the stress field at the rim should open and close fractures, so that we see young crevasses aligned roughly normal to the gradients of change. If outgassing from deeper layers ever joins the cycle, we should find pitted textures and subtle mounds where gas once percolated and lifted the surface. Each of these ifs can be made into a map and an equation, not just a thought. This matters because climate can exist with almost no air. The machinery of exchange does not require sky-filling clouds or roaring fronts. It needs a volatile, a gradient, and time. Worlds we once wrote off as inert may have climates that whisper rather than shout. Our tools must learn to listen. We test with repeat imaging and patient timing. We ask the camera to return to the same rim at the same season. Then at the opposite season, we ask spectrometers to check grain sizes and phases to find where frost is youngest and where it is old. We ask radio science to feel for minute changes in gravity that betray mass migration within the shell. We ask occultations to tell us how pressure flips with season and with geography. Each instrument is a finger on the wrist of a sleeping giant, counting beats that most would miss. We also court the interior. If convection cells are the right size and speed, the basal temperature must approach the melting point of the mixture there, whether it is pure water or brine spiked with ammonia and salts. If the crust shows extensional tectonics rather than compression, then the shell may have thickened as the interior cooled, or the interior may have expanded as water froze to a less dense phase. Cracking the skin. A lens of liquid beneath the basin would fit both clues, stabilizing the depression and feeding slow uplift at cell centers. How would we test a breath on a timescale this large? By watching its footprints on the ceiling. This matters because small planets and moons can host long-lived engines. You do not need a huge core or a blazing sun to keep process alive. You need materials that change phase, a geometry that collects those changes, and a lid that holds the story together for ages. The heart basin is geometry, material, and lid in one lesson. A final line of pursuit connects the lung to the sky. Molecules launched from the plane should feed the haze layers that ring the limb like stacked glass. The thickness and altitude of those layers should vary with the vigor of the lung. If the plane exhales more strongly in one season, the middle layers should brighten or rise, because the atmosphere warms in the band where those molecules break apart and recombine into more complex particles. If the lung rests, the layers should flatten and dim. This is not sentiment. It is a testable chain from ground to sky. This matters because it shifts habitability underground and under ice. We are not claiming life. We are claiming storage, chemistry, and persistence, the ingredients that make some worlds worth the extra weight. A system that cycles energy through cold chemistry is a system that remembers, and memory is the first gate to complexity. If the lung is real, it has neighbors. There should be small vents or domes at its margins where deeper volatiles sometimes join the dance, leaving bulbous hills or moats where material rose and settled. There should be fans of fine grains that record prevailing breezes spring by spring. There should be terraces where the plane once stood higher and then slumped, a ledger of old sea levels written in frost. None of these features alone proves the breadth. All of them together outline a chest that rises and falls. This matters because exchange between world and moon can shape both bodies. If vapor is lost to space and caught by the companion, roofing it with red chemistry at a pole, then the lung is not just local weather. It is a bridge of matter, a system-scale exporter of change. A small world can reach out and touch its partner with the lightest of hands. We end the chapter with the shift from metaphor to measurement. The lung is a picture. The plane is a machine. The world is an engine room that runs on slow sunlight, tiny pressures, and the reluctance of nitrogen to sit still when warmed. In the next chapter, we use the one instrument that never tires and never lands to watch the machine at work. We use light that slides along the edge to reveal the shape of the air and the pulse of the ground, because the veil that glows at sunset is the map we need to read the breath. To follow the lung, we must read the veil of light that wraps the world. At sunset on that world, the limb becomes a blade of silver. Then the silver thickens into rungs that climb the sky. Pale bands stacked above the dark curve. Peaks bite into the glow and cast needle shadows straight into space. The scene is quiet, but the geometry is not. The air, though thin, arranges itself into layers you can count. Each layer brightens, then fades. then brightens again as the sun slides behind the rim. It is the first clue that the atmosphere is not a smear. It is an architecture, a cathedral of haze. The contradiction comes quickly. How does air this thin build architecture? How can so little material produce such bright edges? A hint lies in how light prefers to move through small particles. When the sun sits low, rays pass through the haze and are bent forward. The particles are not mirror bright, but they send light toward us in a narrow cone. Forward scattering turns a faint atmosphere into a luminous skin. The layers become visible not because they are thick, but because their grains are good at guiding light in this one geometry. If nearly nothing can glow like this, what else hides in the nearly nothing? In plain terms, the glow is a trick of small spheres set in a ladder. Each rung is a band where temperature and chemistry select a certain size of grain. The band above it prefers a slightly different size. As sunlight warms and cools these bands, particles grow, settle, or float. The result is a stack with rhythm. That rhythm is the measure we need. If a layer rises at dusk and drops before dawn, the shift tells us about heating and cooling rates. If a layer tilts over a mountain and flattens over a plain, it tells us how winds and waves run along the surface. We can test this with three kinds of observing. Limb imaging at high phase angles shows where layers are brightest and how sharply they bend. Stellar occultations reveal the pressure profile, so we can anchor brightness to density rather than guesswork. Phase curve measurements at different wavelengths tell us particle sizes and shapes, because color and angle together constrain the way grains scatter light. When these pieces agree, we can say more than that there is haze. We can say what the haze is made of, what it is doing, and how fast it changes. If the stack is so orderly, who or what rings the bell that keeps time? A likely bell is the ground itself. Mountains launch gravity waves that run upward like ripples from a stone tossed into a pond, except the pond is air and the ripples travel vertically. Where waves crest, air expands and cools, and fine particles condense. Where waves trough, air compresses and warms, and particles evaporate or fall. The pattern locks to the terrain. That is why the layers bend over peaks and dive into valleys. Now the cathedral makes more sense. The arches are wave fronts. The aisles are invisible lanes in the wind. Do we see the same arches at different seasons? Do their heights change with the position of the sun? The haze does more than glow. It negotiates the energy budget. Particles absorb sunlight and re-radiate heat. They shade the ground by day and keep it slightly warmer at night. This is feedback. A stronger haze can cool the plain beneath it in the afternoon, which slows sublimation, which lowers the supply of fresh grains that would otherwise thicken the next day's haze. A weaker haze allows more light to strike the ground, which speeds sublimation, which loads the air with new molecules that may form more grains after they climb. The lung in the chapter before and the veil here are partners in a slow dance. If the partners change step, which one leads? Why this matters is direct. A layered haze is a free thermometer and an altimeter. It records heating and cooling in stripes we can photograph. It shows how air moves when pressure is almost nothing. It turns the limb of a small world into a meter we can read from millions of kilometers away. It gives us a way to watch climate without clouds or storms. We study the striations like geologists study rock beds. We measure their spacing and their sharpness. We trace a given band around the disk and ask where it bends and where it stays flat. If a band lifts over a certain range of peaks, we know those peaks push waves of a certain strength. If a band breaks at a canyon, we know the flow drops through that gap. This is not art. It is tomography by sunset. Why trust shadows when we can send a probe? Because shadows carry information across large areas at once. Another line of evidence comes from color. Near ultraviolet light exaggerates fine layers. Redder light penetrates deeper before scattering. If the blue band brightens first, small grains dominate high altitudes. If the red band brightens lower down, larger grains or clusters must be forming there. That vertical gradient is not cosmetic. It encodes chemistry. The same reactions that grow haze can seed the red organics that will later settle out, drift across space, and paint the pole of the companion. Can we use the color rhythm in the veil to predict the color of snow that falls beyond the world itself? Simply put, the veil is a production line. Molecules rise from the plane, break under sunlight, recombine into chains, cluster into grains, and step down the ladder until they are heavy enough to fall. Each step has a tell. Each tell has a signature in brightness and color. Each signature can be measured with a careful sequence of images at different angles and wavelengths. Once the production rates are in hand, we can link the factory in the sky to the stains on the ground and to the red crown on the moon. Why this matters is broad. Thin atmospheres are common. If a haze can shape climate in thin air, then many small worlds inherit not silence, but slow tone. It means temperate control without weather as we know it. It means deposits that look like snowfields but carry the fingerprint of space chemistry. It means we must expand the list of processes that keep surfaces fresh on long-time scales. There is also timing in the veil that reaches farther than a season. The axis of the world tilts. Distance from the sun varies. Over long cycles, the energy budget shifts. Layers that live at one height in one era may migrate in another. If we read the history etched in dunes and plains below, and the oscillations above, we can reconstruct the phasing of breath and glow across centuries. Could long cycles synchronize the basin's pulse and the veil's brightness so tightly that one can predict the other? To follow the chase, we need predictions that can fail. If gravity waves from mountains sculpt the layers, then bands should echo the pattern of the range. If tides from the moon affect winds at certain hours, then bands should tilt slightly toward the line that connects the two bodies. If a burst of sublimation after local noon seeds fresh grains, a mid-altitude band should brighten with a repeatable delay. These are crisp and practical. We can test them with the next pass of a spacecraft or with long baseline monitoring from Earth, timed to catch the same geometry. Why this matters is practical. It lets us plan where to aim instruments and when. It tells us which latitudes carry the strongest signals. It gives us confidence that a single good season of data can be stretched by physics to predict another. That is how small missions extract large science. That is how a slow world becomes readable on human time. There is a human-scale echo of all this. Stand on a ridge at dawn and watch fog in a valley. It divides into sheets. It ripples as a light wind crawls across the fields. It thins on one slope and thickens on another. The pattern reveals the shape of the ground without a map. The veil on that distant world does the same trick for us. Only cleaner, because dust storms do not scramble it and trees do not stir it. It is the pure form of a phenomenon we already know with our own eyes. Does that make it easier to trust? We also ask a question about the top of the veil. How high do the layers rise? High enough that sunlight shatters molecules before they can cluster. High enough that the air is almost a vacuum. There, the grains are born and die quickly. The middle levels are the workshop where clusters grow sturdy. The low levels are the loading dock, where grains accrete frost and sink. If we can separate these floors by watching how quickly brightness responds to a change in sun angle, then we can write a vertical schedule for the entire factory. That schedule is a window into the chemistry that feeds the distant moon. Why this matters is strategic. If the veil is the bridge that moves matter from world to space, then its strength sets the budget for the whole system. A heavier veil means more export. A lighter veil means less. The red cap on the companion is a ledger entry written in organic varnish. By reading the veil, we read the budget before it lands. A final reveal sits in a simple limit. Layers that are too sharp for their environment imply a supply of tiny seeds renewed constantly. Where do the seeds come from? One path runs through small outbursts at the edges of the bright basin. Another runs through the day-to-night flow that lifts the lightest molecules preferentially, which then build the first clusters. A third possibility is breaking waves in the upper atmosphere that tear larger grains into fleets of smaller ones. Each path leaves a different pattern in the veil. We do not need to guess the winner. We can let light decide by watching which pattern appears and when. Why this matters is philosophical as well as technical. The veil is not a barrier that hides the world. It is a script the world writes about itself in light. For a patient reader, it is candid. It admits weakness and strength, pause and surge, order and error. It even tells us when it is being rewritten by forces beyond the local, such as the slow turning of the orbital year. Reading that script aligns us with the clocks that rule small worlds. It trains us to think in spans that match the subject. This chapter stays with a single metaphor on purpose. The cathedral is the right one. The arches are bands. The nave is the clear air between them. The clerestory is the upper levels where light runs unhindered. We are not tourists in that building. We are surveyors. We count stones, not steps. We measure angles, not awe. The awe will be there anyway, after the numbers fit. By the time the veil is mapped, the story points beyond the air. Particles that survive the descent fall as frost and dust upon the plain. Particles that escape drift until gravity catches them on the neighbor world. There they wait under weak light until chemistry deepens their color. From our vantage, the result is a polar stain that refuses to fade. If the veil is a factory, the red cap is its exported work. To trace that work back to its line, we now follow the color to the twin-locked companion and the story of red snow. A red stain crowns the pole of the companion, a thin varnish that refuses to fade. It lies on old ice like a film of dried paint, more saturated near the center, more diluted toward the rim. And it turns the pole into a compass needle we can see from afar. The world and its moon face each other without pause, locked so tightly that their shared center of mass hangs in open space between them. That geometry fixes a permanent day on the same hemisphere of each, and it creates cold traps at the poles where the sun skims low and heat leaks away. If a varnish collects without wind and without rain, where does the feedstock come from? If the pole is a trap, what bait does it use? The first clue is the veil we mapped in the last chapter. Molecules rise from the bright basin on the primary, break under sunlight, and recombine into complex strands that darken when cooked by radiation. Grains grown from those strands scatter blue light and absorb red light. So to our eyes, their accumulation looks rusted or wine-colored. They are not paint. They are the ash of chemistry. The second clue is the escape route. Some of the molecules in that thin air have just enough energy to climb above the world and drift along ballistic paths. They do not form a wind as we know it. They form a tenuous rain of molecules and grains that can cross tens of thousands of kilometers if gravity lets them. The third clue is the lockstep dance. The companion's pole points through long spans to cold sky, making a freezer where particles that arrive are more likely to stay than to rebound. Does this triad suffice to explain a polar crown? Now the contradiction. Why is the stain mostly at one pole? Why not two? Why is it concentrated in a halo instead of in bands at various latitudes? Why is it stable over what appears to be long intervals when it sits on ice that should creep? The simplest local source, cryovolcanism from the companion itself, would tend to place deposits along fractures or vents, not paint a cap with such symmetry. The simplest external source, a stream of dust from space, would not care about the planet-moon pairing, and would not time the delivery to the dance of atmosphere and season. If neither naive source fits, what does? At its core, the current working picture is an exchange. The primary exhales. The companion inhales. Methane and nitrogen leave the basin as vapor, climb on warm days, and some portion escapes. In sunlight, those molecules break apart and rebuild into heavier compounds we call tholins. The lightest are blown away by radiation pressure. The rest follow the gravity of the pair and drift until the companion's polar cold trap collects them. Once caught, they darken further under ultraviolet and charged particles, producing the red tone we see. It is a wind-blown lacquer, built layer by layer in a slow workshop that spans two bodies. Does such a spare machine really run on so little input? We can test the lacquer. Spectra of the cap should show absorption features of complex organics superposed on water or ice mixtures. The color should deepen with residence time toward the center of the coldest region. The particle sizes should be small near the surface and larger where sintering and frost rebinding have had more time. If the source breathes with season, the cap should grow more in one half of the orbital year and pause in the other, producing faint rings that a careful camera could detect. If the delivery is directional, linked to the orientation of the primary at escape, there should be a slight azimuthal asymmetry in stain thickness, a fossil trace of the prevailing transfer route. Would those asymmetries be strong enough to see across the gulf? There is also a way to check the budget. The mass of red material can be estimated from reflectance and grain size. Dividing by plausible accumulation rates gives an age. That age should be in rough agreement with the age of other young features on the companion, such as fresh craters that have not yet been coated to the same degree. If the cap is young compared to the surface beneath, the exchange is ongoing. If the cap is old and saturated, the exchange may have faded. Either outcome tells us about the engine on the primary. Either outcome can be falsified by better data. How old is the varnish that stains an airless pole? This matters because it proves that small systems trade mass in quiet ways. A thin atmosphere can reach across space and lay down a visible sign on its partner. Not as a storm, but as a whisper. It turns a moon into a ledger. It tells us where the balance has moved over time. It upgrades the word system from geometry to commerce. The lacquer also changes physics at the surface. Darker areas absorb more sunlight and warm slightly above surrounding ice. That small contrast influences what frost survives the day and what sublimates, creating feedback loops that sharpen the cap and keep it centered. A warm skin may soften the topmost millimeters, helping grains sinter and lock in place. Over decades, the stain can become a thermal regulator for the pole, a skin that keeps itself alive by amplifying the difference it creates. If color can shape temperature and temperature can shape color, how far can this loop run before it saturates? This matters because color drives climate in thin air by small amounts that matter over large timescales. The cap can steer trace flows of gas, reroute where hoar deposits, and set the stage for where cracks open or close as the shell expands and contracts. On a world without weather as we know it, tone becomes force. We will not pin our case on color alone. We will ask for texture. Under magnification, wind-blown lacquer should look like fines cemented by frost, with tiny bridges between grains. It should mantle rocks and the walls of shallow pits with a uniform thinness. It should lack the bubbly, hummocky textures that cryovolcanic lavas of water or ammonia-rich slurries would leave. Its thickness should increase smoothly toward the coldest point rather than in patchy fans. If we see that geometry, we can hold our theory more confidently. If we do not, we must revisit the source. There is another lever: dynamics. The locked dance means that the same face of the companion sees the primary. That geometry focuses any ballistic rain toward longitudes facing the partner. But the polar cold trap sorts by latitude. The result is a cap that is not perfectly circular, with a slight bulge toward the sub-primary point. If mapping shows such a bulge, it is an elegant confirmation that the transfer is directional rather than isotropic. If it is absent, then either the atmosphere escapes symmetrically on average or the cap has been smoothed by local processes that erase the hint. Which kind of symmetry do we live with here? This matters because directionality encodes cause. A pointing stain acts like an arrow back to its source, letting us distinguish between endogenic and exogenic gifts. On small worlds, almost every process is subtle. We cannot afford to lose any arrow. We also need to rule out or quantify internal sources on the companion. It could host its own pockets of release through ancient fractures, with trace outgassing that would paint the pole from within. If that is true, we should find aligned lineaments, local bright halos where fresh frost has erupted, and spectral signs of the specific volatiles involved. If we do not, the external case grows. The absence of local vents is not proof by itself, but it tightens the net. Think of it like this. You clap erasers together in a still classroom and the finest chalk drifts to your neighbor's black coat. You did not throw the dust on purpose. It traveled because the air carried it and the fabric trapped it. The red pole is that black coat. The primary is the eraser. The room is space. The trick works because of patience and because of the way surfaces welcome or reject what the air delivers. This matters because the same transport can operate anywhere. A small atmosphere brushes a neighbor. Other moons in other systems may wear caps that point back to masters we cannot see. Exoplanets in tight pairs may trade chemistry that we mistake for native soil. The rule expands our search for signatures we once wrote off as isolated curiosity. To chase down the last uncertainties, we ask for time series at a few key wavelengths, for mutual events when the two bodies eclipse each other, and for sensitive imaging of the cap's rim through seasons. If the rim migrates with an annual pace, the climate loop is alive. If spectral slopes steepen during high supply years, the factory in the sky has spun faster. If the cap creeps over an older crater and mutes its contrast, we can measure a rate by comparing before and after. The beauty of a wind-blown lacquer is that it records its own speed in layers we can read. This matters because it turns a distant stain into a chronometer. In a place where clocks are few, any new timepiece is priceless. Accumulation rate, darkening rate, and rim advance together become a calendar we can hang on the wall of that polar hall. The reveal is not only that the cap is imported, it is that the imported film is part of a larger exchange that closes loops across the pair. The primary loses a little of its air to space. A fraction is caught by the companion. The companion develops a cap that controls its own microclimate. Some material may then return in the opposite direction as sputtering or micrometeoroid impact lofts grains away. Over very long spans, the direction of net trade may even reverse as orbital cycles modulate cold traps. Two worlds write on each other. Two worlds read what has been written and adjust. In such a system, surface and sky cannot be studied in isolation. They are one long sentence. This matters because feedbacks across bodies are an unexpected source of order in the outskirts of a system. We learn to look for faint couplings and to respect them. We learn that habitability, in the broad sense of storing and cycling energy and material, can be a property of a duet rather than a soloist. There is one more testable prediction. If the cap is made from airborne precursors, the colors should be deepest where the polar vortex, if any, corrals air for the longest time. Subtle wind streaks should radiate toward lower latitudes where transient flows spill out on rare warm days. On the fringe, we should find an annulus where grains mix with local frost to produce a paler tone with larger, more angular particles. Careful polar traverses in brightness and grain size can, together, reveal the shape of the invisible wind. We return to the beginning. A red cap is not a curiosity tacked on after the fact. It is a map of a process that touches both members of the pair. It hints at an engine on the primary that fuels the veil. It invites us to follow the chain down, from airborne precursors to surface sinks, from drift to deposition, from color to heat, from a quiet pole to the question of where the molecules begin their trip. To learn that, we have to leave the sky and study the ground up close, where domes rise and seams split under pressures too small to hear, yet strong enough to build mountains the slow way. To explain the source of the lacquer, we must search for quiet fire in the ice. Two broad rises swell from the plains, their sides dull and blocky, their crowns sagging as if the roof of a kiln had cooled and sunk. One has a rim like an interrupted ring, with terraces that step down into a shallow bowl. The other looks younger, with flanks made of knotted hummocks and flow like lobes that freeze in place before they can stretch far. There are few scars from impacts. There are gentle moats at the bases, as if the ground once lifted and then relaxed. We are used to volcanoes that roar. Here the shapes whisper, if nothing is hot. Why do these forms look like chimneys? The first clue is the mismatch between shape and weather. There is no thick air to carve cones by rain. There are no rivers to bite channels into flanks. The piles do not sit at the ends of obvious landslides. Instead, the slopes are built from units that resemble frozen sheets poured one atop another. At the crests, pits are aligned along arcs, as if the roof of a vault had collapsed into an emptied space below. On Earth, calderas follow that rule when magma chambers drain. On this world, the chamber would not be a furnace of rock. It would be a pocket where water-rich slurries or ammonia-laced brines once rose, lost pressure, and froze. If heat is faint, what lifted any fluid at all? The contradiction is the cold. Measurements tell us the surface sits far below the freezing point of water. Sunlight is too weak to power geysers for long. Rays from the companion are steady and small. Impact heating would have faded quickly. Yet the terrain is not old and pitted. It is patched by young flows. It is crowned by hollows that look like roofs that fell. How do you square youth with cold? The breakthrough is to reframe what counts as a flame. A kiln is a container that builds and releases heat slowly, and it cracks when its contents change phase. A shell of ice is such a container. Inside, heat from the slow decay of heavy elements leaks outward. Water laced with antifreezes melts at temperatures far lower than pure water. Pockets can form where the shell is thicker or where salts concentrate. If a pocket warms enough, buoyancy does the rest. The slurry rises through fractures as a plug. When it reaches lower pressure near the surface, gases come out of solution and the mixture expands. The plug lifts the roof, spills, then chills and stops. The roof settles. The crack propagates. The cycle waits for the next pulse. To put it another way, the cold flame burns by freezing and expansion, not by fire and ash. This matters because it gives us a complete machine from small inputs. Slow heat becomes organized motion when geometry and composition cooperate. It shows that a world does not need a core like Earth to build mountains. It needs a lid that holds heat, a solvent that melts early, and a way to focus stress. Such machines are common in the outer system. If we learn the rules here, we can apply them elsewhere. We now chase tests that can separate a cold kiln from a heap of debris. If cryovolcanism built these rises, then the flanks should show flow fronts with consistent thicknesses, stacked like shingles. Grain size should change with distance from vents, finer near the crest where cooling is rapid, coarser downslope where the material had time to anneal. The moats should contain rafts and blocks that rotated as the ground subsided, a sign that the roof sagged into voids. The terraces at the crowns should be concentric and broken by radial fractures where the roof failed, not by random polygons. Spectra may reveal traces of ammonia hydrates or salts that refuse to hide at these temperatures. If we find those signatures in the right places, the kiln stands. Why this matters is immediate. A confirmed cold kiln implies reservoirs that store heat and solvent. Reservoirs support cycles that run longer than any season, and they scale up the time window during which chemistry can mature. That is the sort of stability we look for when we talk about potential habitats, even if the habitat is locked beneath armor. We also test with geometry. The rises sit near the margins of the bright basin. That location is a stress amplifier. The basin loads and unloads mass as frost shifts with season. Stresses at its rim should open and close fractures on a clock we can model. If the kiln drew its feed from depth, it would exploit those fractures. Alignments of pits and vents should point along the direction of maximum tension. Flow lobes should drape downhill from those lines. If the lines match the predicted field, the kiln did not pick its spot at random. It listened to the stress. There is a second, slower channel for uplift. Warm parcels in the deep ice shell rise as dye appears. Soft bulbs that carry heat upward without breaking through. When they meet a brittle top, they flatten, spreading into domes and pushing the surface into low, broad hills. If the two rises sit over such bulbs, the outer flanks should be smoother and more symmetrical than explosive vents could achieve. The interior would still host pockets of melt and salts. The difference is pacing. Vents are pulses. Diapirs are tides. Which pattern do the terraces record? Think of the kiln during a long firing. The clay inside expands and contracts. Hairline cracks appear. They lengthen, stop, then link with neighbors. The lid creaks. A small puff escapes. Then the kiln returns to silence. Over time, the vessel shows a net of fractures that remembers every heating cycle. The rises here carry that same net on their crowns. It is a record of many small breaths, not one great exhale. That is why the landscape feels alive without storms. This matters because it teaches us how to read time from form when clocks are absent. Spacing of terraces, spacing of radial cracks, and the depth of moats can be inverted to yield the pressure changes that lifted the roof and the time it took for the slab to fall. If we can assign even approximate numbers, we begin to place the kiln on a calendar that links to the lung and the veil we mapped earlier. A key prediction follows. If vents or diapirs supply vapors to the thin air, then the haze above these rises should brighten subtly at certain hours, not everywhere at once, but in patches that repeat, limb imaging at high phase angles. When the sun rakes across the edge, can catch those brightening events. They would not be plumes like those on a moon of Jupiter. They would be faint, wide, and transient. If we see them, the veil and the kiln share a pipe. We ask for other fingerprints on the lee sides of the rises, where winds slow, fine grains should settle into aprons with stronger signatures of complex organics, because the kiln feeds the factory in the sky with precursors. On the windward sides, grains should be swept clean, exposing fresher ice. In moats, we should find pits whose floors are mantled by frost thicker than nearby plains, because cold air pools there at night. If these contrasts hold, they prove that ground-shaped sky at scales we can map. This matters because it turns morphology into a sensor network. Each hollow, each rim, each apron registers the passing of a pressure wave. If we read them together, we reconstruct flows we cannot yet sample directly. The world becomes a self-logging lab, with features as instruments. There is a question that reaches into the interior. Can a buried ocean feed the kiln? A continuous lens of liquid is not required for every rise, but a regional reservoir beneath the basin would make the whole system easier to explain. Liquid would gather beneath thick crust where pressure and salts keep it stable. From there, warm tongues could rise along fractures into the bases of the rises, concentrating volatiles and making eruptions more likely. If the ocean connects to the kiln, its signature should appear in the chemistry of frozen flows. A higher fraction of salts at the surface would be a clear sign. Purer water ice would argue for local melt without a deep source. Which signature lies on the slopes? The chase is careful because the wrong analogies tempt us. These are not basalt cones. These are not ash fountains. They are slow engines that trade in joules saved over ages. So we propose a set of falsifiable claims. If the rises are kilns, crater counts on their flanks should be lower than on nearby undisturbed plains by a clear margin, implying resurfacing in the last few tens of millions of years. If they are kilns, thermal inertia should differ across flow units, with younger lobes holding heat a little longer into the night. If they are kilns, the alignment of pits should cluster around arcs centered on old vents. If they are not, we will find random patchwork instead. This matters because it anchors speculation to maps and numbers. In the outer system, we will always have more theory than time at the telescope. Predictions keep us honest. They tell us where we were wrong without ceremony. There is one more lever that raises confidence. Gravity fields sense mass deficits under the rises. A chamber that drained would leave a soft negative anomaly. A diapir that stalled would leave a subtle positive one. With careful tracking during a flyby, we can measure these hints. The signal will be small, but even upper limits help. A null result forces us to accept thick stacks of flows without voids, which would favor slow extrusion over hollowing and collapse. A non-zero result strengthens the case for pockets and roofs. Either answer improves the model. So what is the reveal we are ready to hold? Quiet fire is real enough to have built architecture. It does not glow. It does not smoke. It reshapes by lifting, spilling, and freezing, then by letting the lid fall. The pattern is not violence, but patience. The rises stand as chimneys of a kiln that cracked and healed many times, drawing feed from a deep store that cannot be entirely solid. Some of the vapor that escapes joins the veil, which in turn seeds the red that coats the pole of the companion. The kiln thus completes the circuit, interior to surface, surface to sky, sky to space, space to the twin. This matters because it closes the loop between heat and color. It means we can walk a chain of evidence from motes at the base of a hill to a stain on a world hundreds of thousands of kilometers away. It means the engine that turns the heart basin into a lung also primes the kiln to breathe on longer scales. It means that when we look for seas under ice elsewhere, we should look for kilns near basins and for thin veils that brighten over them, because the trio likes to travel together. The kiln metaphor is enough for one chapter, so we fix it in place. The kiln is cracked, therefore the lid has moved. The kiln is cracked, therefore expansion worked. The kiln is cracked, therefore fluid existed, even if only as brine or slush. Each therefore is a test. Each test can be run by a patient mission. We do not need drama to learn. We need orbits that repeat, cameras that return, and spectra that stand up to arithmetic. If this is the face of cold fire, what lies beneath it that keeps the embers from dying, and how large a sea must sleep below to feed chimneys for so long? The fractures look like handwriting stretched across a frozen world. Long grooves run straight for hundreds of kilometers, grab younger planes by the sleeve, and continue as if nothing could stop them. Ridges stand beside troughs that gape just enough to hint at missing volume. Now and then a scarp drops cleanly, and a narrow valley opens like a seam pulled apart. There are few features that press the crust together. Most pull it open. If the shell is expanding, what inside it is making room. If the surface is being stretched, what down below refuses to shrink. We begin with the puzzle of energy. Sunlight is thin, impacts are rare, tidal work from the companion is steady but small. Yet some terrains look young, with scant craters and fresh edges. The simple answer, that everything here is ancient and static, does not match the map. The bolder answer, that heat hides inside and works slowly, fits the pattern better. Where could such heat come from, and how does it avoid leaking away? At its core, the deep layer is not rock and not empty. It is likely a reservoir where water stays liquid with the help of salts and other antifreezes, sealed beneath kilometers of ice. During the body's violent birth, heat from impacts and compression would have melted much of the interior. As time passed, the outer shell thickened into armor, but the inner tank did not freeze solid. The rock and water interface still releases heat from slow radioactive decay. Dissolved ammonia and salts keep the melting point low. If the lid is thick, it traps heat like a blanket. If the lid is uneven, heat prefers certain routes, and those routes draw lines we can see at the surface. Is a warm tank under glass enough to stretch a world? The geometry argues yes. When liquid water turns to high-pressure ice at depth, it expands or contracts depending on the phase. If an ocean slowly freezes into phases that take more space, the shell above must respond by splitting and lifting. If a basin on the surface fills with denser ice, the planet can try to roll so that the heavy patch sits closer to the equator, reducing the energy of rotation. Reorientation pulls on the crust. Fracture belts line up with the new stress. In both stories, an internal lens of liquid makes the numbers easier to balance. Does the pattern of grooves and basins match a roll that only an ocean could allow? Think of the ocean as a library under glass. The books are not words, but layers, each holding a record of heat released and salt concentrated. The glass is the ice shell. We cannot open the case yet, but we can press our faces to it and read the arrangement. A library stays in order when the catalog system works. An ocean under glass stays in order when its lid does not break. Everything we see on the surface is an erratum pasted on the cover. How many corrections did time paste? And what do they say? A full test begins with extension. If the crust is being pulled apart, we should see grabens that cross everything in their path and keep their orientation for long stretches. Their walls should be fresh compared to neighboring terrain, in places where the pull was strongest. Faults should bound blocks that dropped intact, leaving flat floors and sharp shoulders. Counts of small craters on those floors should be lower than on the old planes they cut, which would fix a young age. In a world of gentle slopes and slow processes, youth carries weight. If the numbers say young, the engine is alive. This matters because active extension implies a reservoir that can push up and pull down over geologic time. It means the world is not a fossil, but a slow machine. It means energy and material move along paths we can model, which makes prediction possible rather than romantic. The next test is subtle. If there is a decoupling layer of liquid, the solid shell can drift a little over the interior. That drift changes how the body wobbles as it rotates. A free wobble on top of a liquid layer is larger than a wobble on a rigid body. Precise tracking of surface landmarks over years could measure this. Small changes in rotation that repeat in exact periods would argue for a shell that moves independently. If the shell slips, the library under glass is real. Why this matters is strategic. A decoupled shell means that stresses can reorganize with season and with mass shuffling at the surface. It means fracture belts can be reloaded many times. It means a single world contains multiple tectonic episodes written on a moving canvas. We can ask the gravity to speak as well. A region underlain by liquid will influence the local field. The signal is faint, but a flyby that passes just right can detect a hint. A slightly lower gravity over a basin that grew by loss of dense rock. A slightly higher gravity where deep melt moved salt-rich water upward and left heavier phases behind. Either case would sharpen the picture. Gravity is a reluctant witness, but it does not lie. Can we afford to miss a chance to hear it once? What this means is that, with tectonics, rotation, and gravity together, we can sketch the ocean without tasting a drop. We can bound its thickness by the size of its effect. We can bound its salts by the endurance of liquid at given depths. We can bound its extent by the continuity of surface belts. Each bound cuts the space of possibilities in half, until what remains is a narrow lane that a new mission can drive straight down. There is also chemistry to consider. Some reactions between rock and water release heat, consume heat, or alter the mix of salts. If the rock core built clays and serpentine minerals by reacting with water, hydrogen could have been produced in the past, a modest additional source of energy. If the water once held more ammonia than it does now, freezing would have happened slower, and the ocean could persist longer. Laboratory work on these mixtures at relevant pressures and temperatures is slow, but those numbers are the spine of our library catalog. Should we expect the same chemistry on every icy world? Or does each write its own design? This matters because each ingredient moves the goalposts for long-term liquid. You do not need miracles to keep an ocean warm. You need a blanket, a heat source that never goes to zero, and a solvent that plays by the rules of phase diagrams at very low temperatures. The blanket is the shell, the heat source is decay, and perhaps a little chemical work. The solvent is water spiced with salts and ammonia. That trio is not rare. Plane geometry adds another page. If the bright basin on the surface is both deep and filled with low-density ice, the entire body should have turned a little to put that basin closer to the equator. A motion called true polar wander. A roll like that leaves scars. Old fracture belts turn slightly from one region to another. Former equatorial terrains inherit features that used to be polar in nature. If we can trace a great circle that the belts tend to follow, we can infer the pivot. That pivot narrows where the mass anomaly lies below. A mass anomaly of the needed sign and size is easier to form if a warm layer lurks beneath. Does the map agree with the mechanics? This matters because it ties separate clues into a single story. Extension without wander is strange. Wander without a mass anomaly is stranger. A consistent triad points back to an ocean. We can also listen for the ocean with an instrument not yet flown there. Seismology would ring the shell and read echoes from the liquid below. In practice, short missions cannot wait for quakes. They can, however, carry impactors to make gentle taps and record the ring. This is a hard experiment on a small world with long days, but perfected once it can be used everywhere. Do we let difficulty excuse ignorance, or do we prepare the technique now? This matters because the question of liquid under ice will haunt every target on the frontier. A good method to confirm or deny will save decades of confusion. Rhetoric gives way to a reveal we can hold responsibly. The map of extension, the suggestion of wander, the youth of certain units, the absence of global compressional belts, and the logic of persisted heat together favor an interior that did not freeze to the core. If the ocean is present, it is old, not young. It likely formed early and endured, rather than appearing late. A warm start that refused to die is more plausible than a cold start that somehow caught fire. A sleeping ocean is not a dream. It is a file room still locked, with cabinet drawers that slide a millimeter when the building shifts. For more evidence-based space storytelling, like and subscribe to the Quiet Universe channel. We do not rest on poetry. We end with predictions that a mission must be able to falsify. If the ocean lens is thick beneath the bright basin, tides should make the shell flex slightly more there than elsewhere, and repeated imaging could detect tiny shifts in fracture offsets over long baselines. If salts help the ocean endure, the domes and flows nearest to possible vents should show a spectral bias toward those salts compared to far-field plains. If true polar wander did occur, a grid of small extensional features should curve as they cross key longitudes, mapping a great circle that gives back the old equator. If these do not appear, the case weakens. If they do, the case grows tight. This matters because it replaces arguments about names with measurements about nature. A world with an ocean under glass is not defined by a label. It is defined by the processes that storage allows. Heat can be shuttled. Chemistry can be archived. Surface change can be fed from below, rather than only from above. There is a human-scale echo for the patient mind. A lake sealed under winter ice waits for spring. It does not communicate much with the sky. Yet it stores heat and feeds the shore through seeps and cracks. Now stretch spring to 1,000,000 years and thicken the lid to a mountain. The analogy is crude, but the feeling is right. The deep can work in the absence of noise. We close the cabinet gently. The library under glass is not an impossible state. It is the natural endpoint when a small body starts hot, gains a lid, and learns to save. From here, the story flows outward. The factory in the sky that stains the companion requires a long supply of molecules. The lung we mapped in the bright basin prefers a steady source of cold that does not run out. The chimneys in the plains want a reservoir to tap. All three partners point back to the same book in the same shelf of the same library. If the shelves hold the earliest chapters of the system's story, where can we find a copy written before the heavy editing of time and heat began? And how would that original text look if we found it? It sits far beyond the bright basin and the quiet kilns. A small world shaped like two spheres pressed together, flattened a little, fused without shattering. Its surface is softly red, its craters few, its outlines simple in a way that feels ancient rather than crude. The neck between the lobes looks pinched, as if the parts met slowly and never argued. If the inner system writes and rewrites its history in fire, this object is a shelf where the first edition survived. What kind of shelf can keep pages from the earliest chapter intact? What could the pages themselves be made of? The first clues are texture and symmetry. Each lobe shows subtle, onion-like layers that wrap around a center, as though material arrived gently in nested sheets. Those layers line up toward the neck, not randomly, but with a patience that suggests the lobes were siblings long before they touched. Across the surface, small pits are scattered, But deep scars are rare. Nothing here speaks of violent mergers. The color is uniform in broad strokes, a steady red varnish that implies similar chemistry across both halves. If the parts grew together from the same cloud, why did the final step not crush the stories? The contradiction is our habit of thinking in collisions. In most of our models, planetesimals form by a storm of impacts that grind and glue. High speeds dominate. Chaos rules. And survivors are lucky stones in a mill. But a contact world that kept its layers, kept its neck, kept its gentle curves, forces us to consider a different nursery. Low velocities and local collapse must have mattered, because only a slow meeting preserves a neck like that. If the early disk was a racetrack, who closed the track long enough for a quiet handshake? The breakthrough is to accept that dust and pebbles can organize themselves before gravity finishes the job. Gas in the young disk slowed the drift of small solids. Under the right conditions, streams of pebbles crowded together, their mutual drag and turbulence making clumps that grew denser until gravity took over. Two such clumps could form side by side, condensing into two lobes that orbited each other closely. With gas still present to damp motion, the pair spiraled inward and touched. No blast, no spray, just a press and hold. Layers recorded the infall. Color recorded the chemistry. Shape recorded the meeting. To put it another way, the archive is not a relic from a wreck. It is a bound volume from a quiet print run. We can chase this hypothesis with tests only an archive can pass. If layers truly accreted in place, their poles should align with an early spin axis, and their curvature should be smooth, not kinked by later deformation. If the lobes were partners before contact, their layer axes should be offset in a way that remembers the binary orbit. If the neck formed by gentle settling rather than by sandblasting, we should find fine, lineated deposits there, not a jumble of breccia. The tightest constraint comes from speed. The merge velocity must have been near walking pace by planetary standards. We can estimate that speed from how much the shapes flattened, from how far layers deflected near the neck, and from how much rubble spilled, which appears to be very little. Does the math of slow merger fit the neck we see? This matters because it validates pathways of formation that do not rely on destructive chaos. If low-velocity collapse and pebble-driven growth were common, then many small bodies began as ordered stacks, not as shattered piles. That means their chemistry reflects relatively pristine nebula feedstock, and their shapes preserve the flow of the gas and dust that fed them. The archive is not just old, it is honest. Our chase moves from form to number. Measure crater counts on each lobe and compare. If both faces gathered scars at similar rates, then they shared the same environment long before contact. If one is older, then the binary met late. So far, the counts say youthful surfaces by outer belt standards. That supports a gentle environment with low impact speeds and a thin rain of projectiles. We can also weigh the archive indirectly. If its spin is slow and its wobble small, then its internal strength can be low, more like a coherent foam than like solid rock. Low density would agree with the idea that it is a lightly compacted book, not a stone. Does the archive float in our equations as easily as it seems to float in space? In everyday language, this object is two snowballs pressed together without a throw. That image helps for one more reason. Snowballs keep their texture when handled patiently. They lose it when squeezed hard or tossed fast. The archive keeps its texture. Patience made it. Patience kept it. Why this matters is immediate. A quiet archive lets us calibrate chronology. Layer counts and crater counts together can set a pace for dust delivery in the outer belt. That pace folds back into models of how quickly small worlds grow, which in turn informs how fast big worlds needed to reach their current sizes. If the archive says slow, then giants formed with help from gas-assisted drift, not by bare collision alone. If the archive says faster than expected, then our drag and clumping models are incomplete. Either way, the shelf tells the library how loud the reading room was. The map of color deepens the story. Methanol-rich and complex organics coat the surface. reddening it. Efforts to find water ice exposure suggest that fresh fractures are scarce and that resurfacing by avalanches is limited. The chemistry looks steady because turmoil has been rare. That steadiness means the outer belt can cook organics in place for billions of years with only weak stirring. If such cooking happens widely, the belt is not just an archive of dynamics. It is an archive of prebiotic chemistry. How many shelves like this one still sit in the dark, quietly compiling recipes? We also ask the archive to tell us about the geometry of the early disk. The orientation of its lobes and layers points to the flow lines of the gas when it formed. If many contact binaries share similar layer axes and neck alignments, then the nebula that built them had a preferred pattern of eddies and filaments. That pattern is the fingerprint of the disk's turbulence and pressure waves. A single object hints. A population proves. The archive is our hint. The cold classical belt is our proof. Why this matters is strategic. We need ground truth for models that cannot be tested in labs. We can simulate turbulence. We can model collapse. We can integrate orbits. But without a few real fossils to check against, we are fitting curves to our own imaginations. The archive is one fossil we can read in 3D. The chase continues with subtle mechanics. The neck appears free of large compressional folds, which places an upper bound on the contact force. The lobes are flattened, which places an upper bound on their pre-contact spins and densities. The whole body rotates slowly today, which is consistent with gas drag and tidal friction having drained energy from the binary before touch. Every bound narrows the scenario. We are not guessing at magic. We are doing forensics with calm artifacts. There is a final contradiction to resolve. If the archive is so pristine, why is it red and not gray? The answer is that time in vacuum is not silence. Solar radiation and charged particles slowly break simple molecules apart and let them reassemble into complex carbon-rich networks. The result is a deepening red, the same kind of varnish that we followed from the distant world to its moon. That color is both a warning and a gift. It warns us that surfaces evolve even when rubble is absent. It gives us a built-in dosimeter for exposure. If two shelves in the same wing of the library differ in shade, their ages differ or their exposure histories diverged. Color becomes a clock. Why this matters is comparative. With a clock on color and a map of layers, we can compare archives across the belt and rank them by how loudly the nebula spoke in each place. We gain a way to say this patch of the early disk was quiet and this one was choppy. We can then match those maps against the distribution of binaries and singles, flattened and round bodies, to ask whether calm favored twins and chaos favored loners. We do not keep the chapter in metaphor alone. The archive also answers a practical need. Missions beyond the giants live on low power and long patience. Targets with gentle histories keep their information in simple forms. A contact world asks for cameras, not drills, for patient light curves, not seismic networks. That makes it a realistic destination for small craft. The science per kilogram of propellant is high. A fleet of small scouts could read many shelves while a single large mission waits for a window. The archive is not only holy, it is handy. Why this matters is programmatic. If we can show that reading a few more shelves will constrain planet formation theories sharply, those scouts become more than curiosities. They become instruments that shorten debates back home. They will not solve every mystery, but they will close the gap between what we can imagine and what the disk actually built. One elegant thread ties the archive to the duet we left nearer the sun. The same slow chemistry that paints the contact world also paints the pole of the companion. The same low-velocity logic that let the lobes kiss is the logic that keeps grains drifting through the thin air of that other world without tearing it apart. A system that tolerates patience at every scale will leave similar signatures from edge to edge. That is why these far shelves matter to a study of the near pair. The belt teaches us how to think slowly enough. We end the chase with 3 simple predictions. If more archives like this are found, a significant fraction should show aligned layer poles within local groups, reflecting common birth eddies. If contact speeds were low, Necks should lack shock rubble and instead show dust that settled out of micro-avalanches. If binaries formed in pairs and merged late, the ratio of twins to singles should vary with local crowding in the disk, rising where streams crossed gently and falling where turbulence was strong. These are crisp, and they can fail. If they fail, we will admit it and revise the print run. Why this matters is philosophical. An archive is not sacred because it is old. It is sacred because it resists our desire to hurry and demands arguments that survive patience. In a field where dramatic collisions are easy to picture and easy to sell, a quiet shelf reminds us that the universe also builds with a soft hand. It tells us that order is not an afterthought. It can be a starting rule. The reveal is not that the edge holds antiques, it is that the antiques are readable and precise. The small world keeps the cadence of the disk that fed it. The layers hold the signature of gentle inflow. The color holds the tally of exposure. The neck holds the limit on speed. Together, they offer a template, a way to connect chemistry, dynamics, and shape across scales. We can carry that template back inward and lay it over every clue we have already gathered, asking where the same logic applies and where it breaks. The last archive has served its purpose for this act. It gave us a clean first edition to compare with the heavily edited pages near the sun. It taught us that patience was a force, that quiet was information, that low speed could be structure, and that color could be a clock. We will carry those rules with us as we step out of the museum and back into the night to ask what all of this means for us who read by borrowed light. Stand back from the maps. Let the glow on the limb fade in your mind until only its shape remains. A thin script written by a weak sun. Let the lung-like basin slow to a calm pulse. Let the chimneys of quiet fire dim until they are simply forms, not proofs. Let the contact world at the edge become a book closed on a table. All the instruments can rest for a moment. What are we left with? A set of rules whispered by distant ice about what counts as change, about what counts as memory, about how time can be the strongest force in a place where forces are few. We have spent an act following small energies. They push on grains thinner than your hair. They lift frost by the width of a finger. They raise hills over ages with slurries that would not slosh in a cup. If this were only an inventory of minor tricks, there would be no echo to carry. The echo comes from scale. Small pushes with long clocks write in giant letters. Thin air with clean geometry builds a cathedral of layers, not once, but every day. Flows that a person could step across renew plains the size of countries. A fraction of vapor misplaced becomes a climate that arranges itself with the patience of stonecutters. Is there any other classroom in the system where so little teaches so much about the mathematics of duration? We also inherit a different definition of life in a landscape. Not life as biology, life as recurrence. The world we followed refuses to be a snapshot. It is a film played very slowly. Things return, not perfectly, but with enough rhythm to count. A basin breathes. A haze brightens and fades. A pole deepens its color. A pair of hills creak and settle. A library under glass shifts its weight and scribbles a new note on the cover. The lesson is not that we have seen these exact tricks elsewhere. The lesson is that a planet or a moon can be alive to measurement even when it is dead to weather. Can we hold that idea without confusing it with wishful thinking? Pick up the image of the lung and turn it a quarter turn in your mind. It becomes a metronome. The count is slow, but it is countable. Pick up the veil. It becomes a ruler. The lines are thin, but they are straight. Pick up the red cap on the companion. It becomes a ledger. The balance is small, but it is in the black. Pick up the chimneys. They become receipts that read paid in patience. Pick up the archive. It becomes a parchment stamped with the seal of the early disk. Every tool is also a metaphor, and every metaphor can be reversed into a tool again. That is the practical freedom the echo gives. In everyday language, we learned to read a quiet machine. We found a way to see work where motion is almost invisible. We learned that a system can export its story to a partner with dust, can import rhythm from a tide that never breaks, can store heat in a solvent that refuses to harden when salt and geometry protect it, can publish its past to the edge in a body that never knew violence. That is a change in how we approach worlds. We usually arrive with a list of questions that demand noise. Here, the right question demands silence. Why this matters for us is not a riddle. We build our physics on averages because averages are kinder than events. Worlds like this force our averages to include very long baselines. They require models that can sit still for 1,000,000 steps before they show a result. They force our fieldwork to release the habit of expecting a single definitive image and to treat returns like stanzas in a poem. The habit keeps us honest when we point our eyes at distant atmospheres around other stars. We ask whether those thin skies can draw their own layers for the same reasons, whether they can be read at dusk, whether a color outside a planet might be a bill for chemistry that ran for ages before anyone watched. It is tempting to turn this into a sermon about labels. We could argue again about names and classes. That would be a mistake. The echo does not care about our bins. It cares about whether our bins hide patterns. If a world under an old label shows new activations of exchange between surface and sky, that label has become a blindfold. The better task is to sort by process. Where the light writes on the edge, we sort by scattering and particle growth. Where planes turn over, we sort by viscosity and heat flow. Where chimneys settle, we sort by fracture and phase. Where red moves between partners, we sort by transport and trapping. Where archives survive, we sort by speed at birth and calm during growth. The result is a taxonomy that predicts that is what a field needs when it intends to move beyond catalogs. We are also asked to rethink habitability. The word has been stretched by hope until it can mean anything from a wet rock under a friendly sun to a cloud of chemistry in a tide-warmed shell. The echo from the far cold asks for modesty and for care. If habitable means a place where energy is stored and released, where solvents persist long enough to keep a record of their own history, where gradients can power cycles that remain available to chemistry, then the bar is set by patience as much as by heat. A buried ocean with good insulation may be a better candidate for memory than a shallow sea under violent light. If we grant that, then the map of worlds to watch moves outward. A human scale line lands here. A lake sealed under winter ice is still a lake. It accepts dissolved things from the ground. It trades with the shore through unseen channels. It does almost nothing, yet it changes everything nearby. If you look only for whitecaps, you call it dead. If you wait for spring, you call it a reservoir. Which name is better depends on the question you meant to ask. Which question did we mean to ask about the edge of the system? The duet between world and moon sharpened a second lesson. Exchange is not a luxury. It is a rule whenever distances are small and gravity can catch what the sky releases. We learned that color can steer temperature even in very thin air, and temperature can steer where molecules sleep and where they wake. We learned that poles can inherit signatures of a partner's breath. We learned that tide bodies write on each other with pens we can trace back to their inkwells. That lesson scales upward. Two planets in mutual resonance around a distant star will trade angular momentum in ways that modulate their climates. Two moons exchanging frost in a slow ring will build lopsided caps that reveal the sign of the trade. Our eyes are trained for storms. The duet trains them for whispers. The quiet kilns taught a third lesson. Heat is not a single number. Heat is a topology. Energy can pool in pockets because composition bends the rules of melting, because structures trap what would otherwise be lost. That topology is drawn as domes, moats, terraces, and nets of cracks. The pattern repeats in other shells and in other solvents, wherever geometry and mixture team up against loss. There is a chance that small engines will survive on scales that matter to chemistry. We learn to ask not how hot, but how long. Not how much, but how well contained. The archive taught a fourth. There is a regime where birth is not a fight. In that regime, layers carry information about inflow, not about detonation. Necks preserve the sign of gentle capture. Colors preserve exposure. Craters preserve the pace of traffic. When such artifacts exist, they let us tune models of planet growth with more confidence than 30 pages of algebra. It is a kind of grace that the coldest shelves in a system give the warmest clarity about how the room was built. Grace is a dangerous word in physics, but the echo has room for it. Carry these lessons back inward. Ask how many other places we misread because we kept waiting for noise. Ask how many machines we ignored because the knobs were almost still. Ask how many exchanges happen in forms our instruments were not tuned to see. Ask if our own habits of naming and of seeking drama kept us from noticing that we had the needed image already, and it was a backlit rim that seemed too simple to reward another hour of thought. There is another echo hidden in the way we looked. We used light as a pen to draw the shape of air we could not touch. We used gravity as a faint compass to point at voids we could not enter. We used color as an accountant that wrote what passed from hand to hand. We used patience as the fee to enter the stacks. None of those are exotic tools. They are the cheapest things we have. The frontier lets ordinary tools do extraordinary work because the noise is low and the clocks are slow. That is not a reason to be complacent. It is a reason to be bold about simple ideas. We can reframe one more time without repeating. Think of the world with the lung, the veil, the chimneys, and the library as a model of attention. It teaches the patience we will need for ice-rich exoplanets that orbit dim suns, for moons in climates we cannot see, for belts that hold their recipes farther than our lifetimes will reach with ships. It shows that you can measure without touching, that you can infer without pretending, that you can let a metaphor direct you for a page and then fold it back into math without embarrassment. That is not only a method, it is a stance. We also owe a debt to humility. Our instruments catch a handful of photons per second from a rim that glows by luck and by geometry. Our models wrestle with parameter spaces so thin you could slide them under a door. Our arguments risk poetry because the data are spare. The echo answers the fear that we have been telling ourselves stories. It says that stories can be scaffolds. It says that if the predictions in those stories are sharp, if they can fail in public, then the story is not an escape. It is a bridge to a measurement we have not yet made. There is a sentence near the end of every good paper that admits doubt without theatrics. Let us hold to that tone in our films and in our labs. We can end on a thought that folds the map back on itself. The world of the lung can export to its moon. The moon can wear the record. The pair can be read by the light that slides along the edge. The archive at the frontier can tell us how long the press ran before the pair existed. The giants between can be sketched from the way they shaped the belt that kept the book. The whole system becomes a machine that points inward and outward at once, a kind of ring mirror that shows us ourselves at a scale where our rush does not apply. When you see that, the dark is not empty. It is a slow studio where forms are cast with patience and then delivered to any eyes qualified by time. There is a line you can carry out of this, short enough to keep and strong enough to stand alone. We measure worlds by patience as much as by heat. It is not a slogan. It is a rule of thumb that keeps a scientist honest when the obvious path to spectacle would be to shout. To whisper instead is sometimes to tell the truth better. Now the closing image. A small spacecraft has long since flown on. The rim still glows when the sun is right. The basin still breathes under a sky that has no storms. The chimneys still hold their quiet fractures. The companion still wears its faint red crown. The last archive still turns at the edge. 2 pages pressed together forever. In the reflection on the glass of that library, you can almost see us, smaller than dust, holding a mirror of our own and trying to learn the angle that gives the clearest view. What else waits in the slow parts of the universe that we have not trained our clocks to hear? And how must we change our sense of time to read it clearly?